Hello, everybody. Welcome to WALCOM 2022. I am Orgho Bhattacharya. I am going to present our paper, Email Advised Ski Rental Problem with a Discount. Thank you so much for being here today. The roadmap of this presentation is going to be, first, I'm going to talk about what is email augmentation and why it is important for online algorithms. Then I'm going to briefly talk about the traditional ski rental problem. And after that, I will introduce our problem, which we have worked on this paper, which is the ski rental problem with a discount and its properties. And finally, I will explain the algorithm design principles and their benefits. So firstly, the email augmented online algorithm, or what is email augmentation? What do we augment and how do we do that? Before going there, just to briefly introduce what are online decision-making problems. They're an adversary that decides the input sequence and the conventional online algorithm that makes some decisions without any futuristic knowledge about the inputs. We compare the performance of the algorithm with the optimal offline algorithm, which we call OPT, and OPT can see the future inputs. We define a term called competitive ratio, which is the relative performance of the online algorithm to the offline optimal algorithm. And our objective while designing the algorithm is to design an algorithm with the minimum competitive ratio. That means, in other words, lesser the competitive ratio is, better the algorithm is. Now, there are some disadvantages related to such design principles, or in general, online algorithms. Firstly, I would say this is a pessimistic study because we focus too much on some bad inputs, particular bad inputs. And our design principles are like that concerns about those inputs, and our design principles take care of those inputs so that we do not perform worse or do not perform poorly for those inputs. And that may result in poor performance in other cases, which are supposedly easy inputs. So that is one of the disadvantages of online algorithms because of our evaluation and design strategy. And secondly, we do not make any assumption or observation about the input sequence. That means we do not try to deal with the past inputs or try to find patterns in the past inputs, or do not assume anything about the distribution of the inputs. Necessarily, what happens in a simulation with a fairly reasonable real-world data set, the conventional algorithm may perform worse on average than any machine learning algorithm, because the machine learning just does the opposite thing. Instead of putting the focus too much on some particular bad inputs where we don't even know how rare they are or how likely they are to appear, it focuses on having a good average performance. So on the whole set of inputs, possible inputs, it tries to have some performance guarantees on average. ML algorithms. Also, even in the second point, ML algorithms tries to look into the past inputs, tries to predict the future or what is going to be the future inputs. That is also another approach taken care of by ML. And this is why some researchers thought, is it possible to have a sort of stable marriage between online algorithms and ML augmentation? That means, the online algorithms will be designed in a way so that there is also a sort of advisor present, which is necessarily a machine learning oracle, which gives some advice to the online algorithm. The online algorithm may take the suggestion or may not. So, or do some trade-off using this suggestion. So it can do whatever with the suggestion, but there are some advisors there which is coming from machine learning. The algorithms, the advantages that were observed, firstly, it was very good in terms of average performance. And so for all the inputs, particularly for the easy inputs, the algorithm is performing pretty well. And another key advantage is that there are bounded performance for the bad inputs, which we do not have for the original machine learning algorithms. Now, that means basically these ML augmented online algorithms, they bring out sort of the best of both the worlds. One is from machine learning, another is from online algorithm design. These researchers, they found application of this design strategy in several problems, such as competitive paging, job scheduling, membership query structures, such as Bloom filters, index data structures, and so on. So you see, for a large class of online algorithms, this algorithm design strategy found its application. One such problem, which I'm going to talk about, is the traditional ski rental problem. It is a very well-studied problem in computer science. To introduce it briefly, basically a skier makes an irrevocable decision at the start of every day. He wants to optimize between two choices that he has. One is he can rent the ski at a unit price for every day, or he can buy the ski with a higher price and ski for free from then onwards. Although there is a source of uncertainty. The skier does not know in advance the length of the ski session. That means until it does not snow anymore, the skier has no way of knowing that it is not going to snow anymore. This is an example, this traditional ski rental problem, it is a canonical example of rent or buy types problems. Now, let me introduce the problem of this paper, which is the ski rental problem with a discount. Before that, let me talk about the motivation of designing such a problem. The motivation is simply to find application of this strategy to a larger class of rent or buy types problems. For example, let's say there is a return on investment for a market, and the return varies with respect to time. Like this example, in this plot, let's say the percentage of market return, it is 2% for the first 4 days, and from the 5th day onwards, it is 1%. The skier invests the rent that he has not spent yet. Hence, what happens as he invests those in the market, he gets some return. And that means the effective rent, which is the rent he pays minus the return he gets. That effective rent it varies, it is not constant anymore. The way it is going to vary is exactly shown in this plot for this case. It keeps on reducing from the original rent, which he actually pays, which is 1 unit price. From this, so basically, this problem kind of approaches to simulate the net present value of the resource. Here, the resource is the ski. To show this in a more mathematical manner, let's say X is the actual number of days of usage, and B is the price of the ski. The rent is a function that we have, which is basically the rent of the ski for any given day. And so rent of I means rent of the ski on the ith day. And rent X through Y gives you the sum of the rents from the day X to day Y. The way the rent function works here, it can be expressed necessarily as any arbitrary non-increasing function. What it means is that the rent on the I plus 1th day, let's say, is not going to be larger than the rent of ith day. It can be either equal or it has to be smaller than that. Now, let us understand how does the optimal offline algorithm perform for this problem. The OPT, or offline algorithm, that is a visionary. So it knows X, B, and the rent function. We also define another quantity here, which is TB. We refer to that as TB. If you sum, so rent of 1 through TB, it's going to be more than the value B. B is the rent of the scheme, sorry, price of the scheme. And the rent of 1 through TB minus 1 is less than the price of the scheme. Now, the way OPT works, if X is more than TB, that means the algorithm OPT buys the ski on the first day. And if it's less than TB, it keeps on renting. Obviously, because the OPT algorithm, it knows the future. So that means it knows what is the input X. The cost OPT incurs, which is the best possible way to solve this problem, is the minimum between these two quantities, which is rent of 1 through X and B. OPT performs the best because it can see the future inputs. Now, let us introduce the algorithms that we designed here and the design principles and their benefits. The first algorithm we have is the break-even algorithm, which is the best deterministic strategy. It follows the same way that we designed the break-even algorithm for the traditional problem as well. What we basically do is we rent the ski until TB minus 1th day, and we buy the ski on the TBth day. Now, this algorithm, TB is the particular day where we cross the limit of the price of the ski, which is B in terms of rent. That's why we call it break-even. The cost break-even, it denotes the number, the cost that this algorithm pays. It is definitely less than 2 times OPT. That means break-even algorithm is too competitive. Next, we move on to see whether we can use ML augmentation to design algorithms that are performing better in average cases or even in worst case. First, what we do, we introduce an ML oracle that is predicting a quantity Y, which is the proxy of X. And we have a complete trust on the ML oracle. That means we completely trust in the number Y. So that means if Y is greater than TB, we buy on the first day. If Y is less than TB, we keep on renting the ski. Now, see, if Y is actually a very good prediction, that means if Y is almost equal to X or equal to X, that means we basically take every time we take the right decision that OPT will take. That means we are one competitive, or in other words, we are basically as good as the OPT. Now, the prediction might not be as good as we suppose it to be. So the next, the cost when we analyze, that happens to be the maximum of OPT times eta minus 1, where eta is the error in the prediction, and OPT plus R times eta, which is a function of eta. So the cost happens to be maximum of these two in the worst case. The problem is that as the ML predictor fails to provide quality prediction, the performance degrades harshly. And it does not have a worst case bound here. So it can degrade indefinitely and with the prediction failure. That is something bad. So we wanted to do better than that. There comes the next algorithm. Here, the algorithm is ML augmented algorithm with trust parameter. Now, this algorithm introduces a trust parameter. So it's necessarily a sort of tuning knob, which decides how much trust you have on the ML advice. How it works that when y, the prediction is greater than TB, we buy on lambda TBth day, where lambda is the trust parameter, which lies between 0 and 1. And when it is less than TB, we buy on the TB over lambda day. So lambda, because it is less than 1, TB over lambda, that is greater than TB now. So instead of not buying it or buying it on the infinite time, we buy on the TB over lambda here. The strategy is like that. Let's try to understand how does this perform, or what does the lambda represent. And so the cost we incur here is, if we represent the cost as trust is going to be less than minimum of OPT times 1 over lambda, and the other quantity is OPT plus a function of eta and lambda. Now, what this means is that even if the oracle fails to provide quality prediction, the performance does not degrade harshly. Also, the performance is bounded in this case. Necessarily, what lambda represents, or the trust parameter represents here, if it approaches 1, let's say, that means we have less trust in the ML advice. And if it approaches 0, that means we have high trust in the ML advice. Also, in an average case where lambda, we have set it as, let's say, 0.5, that means the trust, which is the cost of this algorithm, the algorithm pays, which is 3 times of OPT. That means for 50% trust in the ML oracle, the algorithm is 3 competitive. Now, let us go to another domain where we have multiple advisors, which is 2 advisors we study here. So what happens here necessarily, 2 advisors are predicting 2 different quantities, y1 and y2. Now the skier is confused because which one to use, which advice to use. One interesting scenario here. One of the predictions, let's say, it is correct, and the skier does not know which one is correct. What can be a strategy in this case? One thing we understand here, if y1 and y2 both are below TB, less than TB, that means the skier should keep renting. And if it's more than TB, then he should buy the ski on the first day. But what happens in this interesting scenario where y1 is greater than TB and y2 is less than TB? We define another quantity here, which is T5. What is phi? Phi is the golden ratio, which approximates at 1.618. So if you sum the rent through 1 through T5, that is going to be greater than phi minus 1 times B. B is the price of the ski. And if you exclude the rent on the last day, which is the T5th day, it is going to be less than that quantity. Now, interestingly, when Y2 is less than T5, then the algorithm rents for Y2 days and buys the ski on the next day. And if Y2 is greater than T5, then it buys on the first day. By doing that, the cost, if we represent it by the quantity multiple, that comes out to be less than 5 times OPT. It does not depend on the error of the other predictor or incorrect predictor. That means the augmented algorithm with 2 advisors perform better than even the break-even algorithm in this case. Now let us move to another problem where 2 erroneous advisors are present. So that means both the advisors, they have some non-zero errors here. In this case, when Y2, which is the smaller prediction, Y1 is greater than Y2. When that is less than T5, we rent for Y2 days and buy the next day. And when Y2 is greater than T5, the algorithm buys the ski on the first day. It does not depend on Y1 at all. And definitely when Y2 is greater than TB, it buys on the first day. The cost that comes out by doing this is a maximum of OPT over phi minus 1 minus a function of eta and 5 plus 1 times OPT. That means that is incredible because the performance of the augmented algorithm with two erroneous advisors that is also bounded by either the error in prediction or the golden ratio. So the performance does not degrade too much, whereas we have enormous advantage in terms of the average performance here. So this is basically what I showed. What we showed in this paper is we used a fairly new algorithm design recipe for these type of problems, for the ski rental problem with a discount. And the scope of like the empirical advantage by doing this for a large class of online algorithms, that scope is always there. We get a bounded performance for the worst case input by doing this. Also, we see we extend this to a large class of ring turbine types problems, and where we can use single or multiple advice to find such advantage. This is where I would like to conclude the talk. Thank you so much for being here, and I shall be happy to answer any questions that you have. Feel free to reach me.